Buenas tardes, and welcome to my presentation on the wonderful phenomena of transition radiation by Matt Farmer. So, the idea of transition radiation is relatively new, with the first paper being published in 1945 by Vitaly Ginzburg and Ilma Frank, and expanded upon by Ginzburg and V.N. Sviatovic, whose full name I literally could not find, the following year, in 1946. There were a few problems with Ginzburg's original theory, despite the math being sound. That is, its applications were incredibly limited. This was the case up until 1959, where Gregory Garibin theoretically determined that Ginzburg's theory, when removed from the limitations of visible light, was applicable in the X-ray region of the electromagnetic spectrum. From 1959 onward, researchers focused on transition radiation using X-rays, where they later proved their theory experimentally, and from there discovered numerous applications for it, ranging from material sciences to astrophysics. The concept is actually relatively simple, and I wanted to cover this before we get into Ginzburg's math. So up on the screen I have a plot in the XY plane on the negative x-axis. You'll see an electron with some constant velocity flying through some media, and by some I mean a vacuum, whose dielectric constant is 1. On the right hand side is some other media with a different dielectric constant. And I want to reiterate the idea that so the electron is moving with a constant velocity in a vacuum with a certain dielectric constant toward a different media with a different dielectric constant. So anyways, the idea here is that when that electron penetrates the dielectric material, that real photons are emitted both into and away from the material. This kind of behavior can be explained by understanding how the electric field of each interact with each other, but the bigger idea here is that from the scattering of photons, you can identify properties of the beam that's incident on the dielectric material. This kind of behavior can also be called transition scattering. So to wrap your head around that, the concept that I gravitate towards immediately is something like Thomson scattering. So like we can calculate properties of an atom from the scattering of the charged particles in that analogy. And I think they share some parallels, not necessarily in the mathematics or like how it's expressed, but in the concept. So Ginzburg describes this as a rather common phenomena, which in my opinion is a strange statement for him to make at the time because we hadn't discovered the applications this behavior has astronomically at the time. But the charged particle in question can't have a natural frequency, and it must be between inhomogeneous materials. So that particular statement is in contrast to something called Cherenkov radiation, where the concept is incredibly similar, but instead the particle is passing through homogeneous mediums. Sorry, it's passing near homogeneous mediums. But I should also mention that we are dealing with ultra-relativistic particles here, so they are approaching the speed of light. So because we have a good foundation of electromagnetism, I wanted to present Ginzburg's own analysis of transition radiation in a vacuum before introducing the more applicable analysis. So the paper that I'll be pulling from is Ginzburg and Sviatocic's transition radiation and transition scattering produced in a vacuum in the presence of a strong electromagnetic field, which was published in 1978. The goal of this is to kind of outline the conditions that transition radiation lives in and make a connection with Maxwell's equations. We are looking at a charged particle moving from a strong electromagnetic field with a constant magnetic field into a medium with no field. All in a vacuum, so we can make those sweet, sweet assumptions. So this is going to feel a whole lot like a homework problem, so bear with me. But on the left, I have a diagram in the x, y, and z directions with the magnetic field vector pointing along the positive z-axis. A charged particle with a mass m is moving with a constant velocity in the y-axis. For simplicity's sake and our purposes, the magnetic field is uniform in the negative y direction and 0 in the positive y direction. So they meet directly in the middle along the x-axis, where we can see the electric field vector line. And what I mean by that is on the left side, so imagine this is a three-dimensional representation. On the left side, we have a uniform magnetic field, and on the right side, there's no magnetic field. Lastly, this bit I don't fully understand, but we need the charge's velocity to be maintained by some external force for these conditions to work, I mean. So that means that the mass approaches infinity as it nears that transition in the x-axis. It's an anonymous external force. For this particular setup, the magnetic field needs to be relatively weak, along with low frequencies for the waves that we're looking at. Our end result is going to be based on the Lagrangian I have up on the screen, where L equals L naught plus L prime. I couldn't find a single thing anywhere about how he came up with this, but I have a few guesses. My own assumption is that this is in order to to satisfy the conditions to carry through the uniform magnetic and electric fields that need to remain constant, which means he probably used a gauge transformation. But again, I can't find where he referenced this in the particular Lagrangian. But anyways, the L naught equation is expressed as the electric field squared minus the magnetic field squared over 8 pi. The L prime is equal to 1/2 x times E squared times the electric field squared minus the magnetic field squared, all squared, plus 7 times electric field times magnetic field squared. And that x is represented by 1/4 pi h bar times the speed of light, and I used script h since I can't find h bar in PowerPoint, over electric charge squared times 1/45 pi times our large magnetic field squared. So I should have clarified. Our B is going to be our weak electric field, and BC will represent our strong electric field. So now to find the polarization and magnetic dipole moment, which is the first step in this scenario. Ginzburg took the partial derivative of that L prime we just talked about with respect to E and B, respectively. And after attempting to learn about tensors for God knows how many hours, I'll just say that the tensors used to find the equations that I have below, these ones right here, were used for the summations between the weak magnetic field and the strong magnetic field. Or in other words, they used a wave field. But in the end, we get these equations for electric and magnetic field, which we can see sit along the x-axis, since we have these IK vectors right here. I'm sure these can be expanded upon, but for right now, I'm just including these ones. So we can recognize a few things about the equations we just found and the setup in general. We know that the magnetic dipole moment and magnetic field depend on each other non-linearly. Our media is inhomogeneous, and we can remember that for most materials, the magnetization is proportional to the magnetic field. From these observations, we can infer that the media is nonlinear. Not only do these obey Maxwell's equations, but we can find the relative permeability of the vacuum if we continued with this method. So I'm sure we've all seen this equation before and we're familiar with it, but to define the variables, M is the magnetic dipole moment, H is our auxiliary magnetic field, B is our magnetic field, X, or script X, is our magnetic susceptibility, and mu is our permeability. So because of the observations that I just mentioned, we know that M is proportional to the auxiliary magnetic field, which means that we can express the magnetic field as such. Since it's nonlinear, that means we can eventually find the relative permeability. If it was linear, then this would be the permeability of free space. But if we were to continue on with this, we would see that we can use the permeability of free space and find an expression for the permeability in the vacuum. But since we're dealing with a moving charge in nonlinear media, why don't we use the Lorentz factor to find a relationship for transition radiation? This is exactly what Gregory Garibian did in 1959 when he found the relationship between the Lorentz factor, permeability, and the intensity of the transition radiation. So in his paper, Ginzburg states that transition radiation can naturally be called resonant transition radiation, and states that effect analogous to transition scattering takes place in a vacuum when a gravitational wave is incident on a immobile electric charge or dipole. If we assume this to apply to the theory of transition radiation, then we can apply phase coherence. Therefore, the mysterious driving force that I mentioned earlier, or that Ginzburg was using in his paper, is replaced by a driving force that has a frequency and a waveform that is coherent with the frequency and waveform of the charged particle that's incident upon the dielectric material that we're looking at. In 1959, Gregory theoretically showed that an X-ray lost energy when incident upon a dielectric material of a different dielectric constant. The energy that was lost was in the form of transition radiation, and this led him to find that there was a relationship between transition radiation and the Lorentz factor. So in order for this to be true, in a vacuum, we need this expression, where epsilon is our dielectric constant for the second media, omega is our frequency, gamma is our Lorentz factor, and theta is our angle of incidence, where 1 is taking the place of our sigma for the vacuum. And for our applications, theta is going to be on the plane, incident on the second media. So the equation I have up on the screen that I was too lazy to type out is derived from Maxwell's equations and is very similar to the equation for intensity that Ginzburg derived, but it takes more things into consideration, including two new things: dispersion and angular distribution. The previous expression that I just showed leads to angular distribution, where theta is the apex angle and is approximately 1 over the Lorentz factor. That angular distribution is in the form of the common shape of transition radiation. So on the top right, there's a conular shape, and I used it to represent what transition radiation usually looks like, and its apex angle is the 1 over Lorentz relation that I'm discussing. So that's taken into account in that above equation, along with dispersion, which is expressed by, or can be expressed through the equation that I have below. That equation is the atomic contribution to the dielectric constant, and it includes polarization and electric field. Because that atomic contribution is dependent on the electric field. The equation I have above is intensity in terms of theta and omega, and it needs to be integrated over frequency and solid angle. And we have one new variable, kind of two. The first is beta, it's the normalized electron velocity, and that also relies on the dispersion equation that I have below, because it accounts for the forward and backward emission of transition radiation. The second, not so new, is theta sub 2. The theta sub 2 is going to be the angle of incidence for the beam in question. But these, using the Lorentz factor proportionality, creates equations that can provide far more information than Ginzburg's limited conditions and his assumptions and boundary conditions. Well, this new set of equations can be used for far more applications. So, in conclusion, I think transition radiation is a really interesting tool that can be used to, one, determine the characteristics of beams, lasers, particles incident on a dielectric material from a vacuum to a different dielectric constant. And the most interesting application, in my opinion, is in astrophysics, where you can actually measure transition radiation and use it to calculate the X-ray emissivity in interstellar clouds, which I need to do more research on, but the potential is incredibly interesting. Otherwise, thank you for listening to my talk, and here are my sources.